Thank you very much. Am I loud enough? Okay, good. First, I want to thank the organizers for inviting me for such wonderful conference. And also, I should apologize about the title. Well, morally, I will speak about, well, three-dimensional, well, morally, right? But at some point, well, the construction will turn a bit more complex, so they will look as multidimensional in some sense, right? I will mostly talk about forcing more than the application. So I'll start just as a warm-up with some basic notions. So when we have a model of CFC, or a finite fragment of it, a model M, and some poset P in M and Q, then we say that P is a complete suborder of Q with respect to the model M, if, well, indeed P is a suborder of Q, and any maximal anti-chain of P that lies in the model M is also a maximal anti-chain in Q. So what's the point of this? Well, if we have two models, M and N, well, where N is bigger, well, where N contains M, and, well, in each model we have the forcing notion P in the model M and Q in the model N, then when P is a complete suborder of Q with respect to the smaller model, with respect to M, what will happen is that the generic extensions will respect the same subset relation, saying that if G is a Q generic set over N, then the restriction of the generic set in P is a P generic over the small model. And, well, and when you look at the corresponding extensions, then the M extension is a subset of the N extension. This allows you to construct, well, in this case, parallel finite support iterations when, well, in this case, it's described that the iteration which lies below is completely embedded in the iteration who lies above. So iterating this process, if you consider two finite support iterations, well, indexed by 0 and 1, such that at the intermediate steps you are always embedded. And when you look at the Qs in the extension at the iterants, then the lower iterants is embedded in the upper iterant with respect to the model, to the smaller extension. So when you iterate posets like this, then you get, yes, a pair of iterations when the one below is embedded in the one of the top. One warning here is that when I consider finite support iterations, I don't think on the first poset, in this case, well, P00 or P10, I don't take it as the trivial forcing. I start like directly with some specific poset and then continue iterating from it. So when we have a pair of finite support iterations, when one is embedded into the other, then we say, well, corresponding to this lemma, we say that this is a coherent pair of finite support iterations. Perhaps this is a basic notion, but, well, the first time the only paper I've seen this explicitly written is in Brendle and Fisher's paper of 2011. So then the basic notion for this talk is this: a coherent pair of finite support iterations. So now the point of the constructions is to give an array of coherent pairs of finite support iterations. And this array will be based on some partial order I. So this is what we call coherent systems of finite support iterations. So we bring this definition in my work with Cy Friedman, Vera Fisher, and Diana Montoya. Well, I should also say that most of this talk is about the work that I made with them in Vienna. And, well, and the second part of the talk is some continuation of what can be done with this. So, okay, so a coherent system, what is a coherent system? So we start with a partial order. So essentially the partial order will index a system of posets that will give you some basis of generic extensions, okay? And once you have this basis of generic extensions, then from each one of the models you construct parallel finite support iterations. So the point is that, okay, this basis, which is in purple, you start with posets, in this case will be like pi0. You start with some pi0 that are embedded corresponding to this order. That means if I is less than equal than j, then pi0 is completely embedded in pj0. So you have an arrangement of generic extensions isomorphic to the partial order. And then from those extensions, then you throw coherent finite support iterations. So the coherent finite support iterations will give you, a system of, how you say like this, of 3 dimensions or the dimensions that you want to imagine this, of generic extensions such that things that lies below are embedded into things that lies above. Or if you want to look at generic extensions, then, vertically, we could say that with respect to the partial order, the BXI model is a subset of the BJXI model. And of course, horizontal, as finite support iterations, horizontally, you get the same subset relation as well. The main point here is that your partial order, your base, typically has a maximum, or at least this is what we consider on our applications. So the point is that we have a maximum, and the point of the whole construction is just construct this finite support iteration at the top. So at the end, what you get, your final forcing extension will be this model here that you get at the top, given by the finite support iteration that you construct at the top. But you just use the lower finite support iterations as a backup to calculate some things that you want to do. So essentially, it's a method to construct a finite support iteration. Okay? So I will explain, generally what are the type of iterations I'm going to consider, at least for the applications in this talk. So we start with some base. Okay, a base indexed by some partial order I. I will consider a top element, right? We start with a base, and from this base, then we construct parallel finite support iterations, or our coherent pairs. So then, of course, these finite support iterations are constructed inductively, step by step, and they are constructed simultaneously. So let's say at the step C, we have constructed all the finite support iterations up to this step C. And then to the step C plus 1, then we extend everything at the same time. This is to ensure that what we actually get is are coherent systems. So meaning that the posets that give your generic extensions are embedded correctly. Okay? So the type of example is this. So the point is to add reals, in this case. So there will be 2 types of reals that I will consider. First, adding a full generic. Okay, so at step psi, when I move to psi plus 1, I want to add a full generic. So what do I mean by a full generic? I want to add a generic real, which is generic from everything I constructed so far at step psi, or meaning a generic real over this top model BMC. Okay, so this is given by definable posets. So if we fix a Suslin CCC poset for this step C, then at each extension IC, successor step IC, we just consider the version of the Suslin poset with respect to the model we are extending. Okay, so these things as Suslin CCC posets, these ensure that we have complete embeddability and that the generic real we are on the top, this is generic over this larger model, and therefore over the larger fragment that I have on the step C. So this is what it means to add a full generic. Okay. The next is adding a restricted generic. A restricted generic will not be like a generic real over the top model, but just over some model in the middle of the construction, or even for some small model that leaves on some of the models. Like you just extend with something that is very small. So in this step, what we do is that, well, we are at a stage C. We fix some coordinates, well, in this reproduction of the partial order we started, we fix some point which lies below the maximum, okay, which in this case we call Txi. And then we look at this model. Then in this model, we choose some CCC partial order. But of course, we want it to be CCC also in the largest models of this stage C. So we demand that in this top model, the CC poset that I construct here, that I have here, is still CCC. Well, this is only because, well, everything, well, or the applications here are just given in the context of finite super iterations of CCC posets. Okay. So then the point is that in this model that I choose, from this model I get some CCC poset, and I just extend in this way. So of course, from the models that are above this one that I choose, I force with this particular, in this case, well, I denote by T, by this forcing T that I choose, okay? So we force always with the same thing. But then in the other models that don't contain all the information that are here to define this forcing T, then for those, of course, we cannot define T, so we just go there with the trivial forcing. Okay. So here, just the technicality here, well, in Brendle and Fisher paper, well, they guarantee that extending like this, well, extending in this form ensure that you have complete embeddability between your posets. So then this is a legal step, like to continue and construct your iterations. So, well, in brief, well, the point is adding, well, generic, full generic, or restricted. So in this case, restricted, let's say that, for example, this is the Heckler forcing for adding a dominating real, just restricted to this model. So if we just repeat this, well, this at the top will be the same poset here, meaning that this is the Heckler for adding a dominating, but with respect to this model. So what we are actually adding is a dominating real, but only with respect to this model. It's not dominating over the model in the top. So use this technique of adding restricted reals. This helps a lot to calculate a lot from, let's say, cardinal models for cardinal invariants. So now, well, I explained like some general construction of the iterations. Now I want to talk about the base structure that are more or less typically used. So, well, just to recall some notation, so for some arbitrary set omega, well, C omega will be, well, the Cohen poset that adds, well, a Cohen real for each member of omega. And H omega is the Heckler's poset adding an almost disjoint family, also indexed by this omega. So this is a CCC poset, and well, and when this gamma is uncountable, well, the almost disjoint family that is added is actually maximal. So why these systems? Well, why consider these posets for bases? Well, first, some typical examples in this context were matrix iterations when you construct two-dimensional arrays of posets by finite support iterations. Well, your base is just a linear order. In this case, well, a well order. So you start with a well order, and from that well order, you construct parallel support iterations, and then you have a matrix of posets correctly embedded. Okay. So in particular, well, this the base here will be just an ordinal, well, a successor ordinal, because I care that there is something on the top. Okay. So examples of some constructions, Blas and Schelauer, they were the pioneers constructing this kind of technique. So the basis there is with co-enforcing. So if you have, your linear order, which is your basis, at alpha, you use the co-enforcing, adding alpha Cohen reals, okay? So then in this vertical section, then you add, a sequence of Cohen reals, and this usually ensures that you preserve some nice set or some kind of, unbounded reals, so on. So this work for the consistency of U less than D in the work of Blas and Schelauer, with large continuum. And now in Brendel and Fisher, instead of co-enforcing, they looked at the Heckler poset adding a math family. So the point was to add in this vertical section a maximal almost disjoint family that you could preserve through your parallel finite support iterations. So through that theory, they could succeed of making A smaller than S in models with large continuum. Well, I should mention also a third example, which is very recent by Dawn and Schelauer, when they constructed also a model with finite support iterations where the cofinality of, where the splitting number is singular. Okay. But that construction is much more complicated as it uses, some more sophisticated forcing posets. And in my recent work with Fisher, Friedman, and Diana Montoya, we introduced three-dimensional coherent systems. But now for these three-dimensional coherent systems, the basis is a square or a matrix of posets, and from this matrix, then we should parallel finite support iterations, forming a three-dimensional rectangle of posets. Okay, so the basis, is a matrix like this, because as we want something on the top, the top will be some gamma times lambda, which gives the dimensions of the matrix, right? Gamma and delta be in ordinals. And the order, we give the order on this block, on this matrix, we give the order just of coordinate-wise order, right? So in our constructions, we consider two types of bases. So one basis of this form. So on one coordinate, we add a math family, and in the other coordinate, we add Cohen reals. Later, I will illustrate this in more detail. Or just adding Cohen reals in both directions. So the point is that here, in the first thing is that in the, let's say, vertical section, or in one direction, you add a math family that you want to preserve, and in the other direction, you add Cohen reals that also help you to increase some other cardinal invariant. Okay. So in some cases, you cannot preserve math families. Like if you start adding full generic dominating reals, then of course you cannot preserve a math family. So in those cases, if you want to forget about A, then we just add Cohen reals in both directions. And still, good applications come from this. Okay. So now one example. Let's start with one simple example when we use this technique. So here, this kappa and mu are regular cardinals, and this lambda could be singular, respecting this cardinal arithmetic property. Then we can construct a CCC poset forcing this, and additionally having a value for having that a value for the almost disjoint number being equal to B in this case. So actually, if you forget about A, this can be constructed by a simple finite support iteration. But in the work, what we wanted to do is to include the value A, even if it's equal to B, but include the value A is in some very common and standard finite support iterations when you separate some cardinal invariants. So this is not a difficult finite support iteration to construct. So for example, to decide a value of uniformity of meager and the covering of meager, First, you know that if you add cofinally mu many Cohen reals, then you will increase this above mu, and this will be lower than mu. But if at the same time you add cofinally full eventually different reals, the eventually different reals will try to increase this and try to lower this. So if you add mu cofinally of these two type of reals, then you ensure that this part will be equal to mu. Okay? Then now this part of making B equals kappa, well, this is not hard because, well, on one side, the eventually different real forcing preserves unbounded families in a very nice way, like in the sense of preservation through finite support iterations. So in that sense, you could preserve some unbounded family of size kappa, right, that you add with some previous Cohen reals. But also inside the iteration, you just want to increase B to be equal kappa. So ensure that you don't have a small unbounded families. So for that, what you do is you just use a small versions of Heckler forcing. So these small versions will ensure that these restricted dominating reals will only dominate fragments, or sets of reals of size less than kappa. So with that, you ensure that you don't have an unbounded family of size less than kappa. And well, and this lambda part here, as well as the Aleph1 part here, it comes from the typical finite support iteration, from the typical theory of preservation in finite support iteration, which is described by the theory in the 90s from from Yehuda and Shelah, and also in other work of Brendle. So for that preservation theory, I will skip everything in this talk. I just want to illustrate like what can you do with this, but somehow skip a lot of technicalities that happens there. So I sort of describe the finite support iteration that gives you this. But then if I additionally want A equals kappa, then what should I do? Well, there are linear finite support iterations. I'm not sure if there are nice preservation theories for that. But if you use Brendle and Fisher preservation theory for math families, then if we reconstruct this as a two-dimensional iteration, then perhaps we could succeed. So this is what we are going to try. Okay, so we start adding the base of this construction will be this well-ordered. When at step alpha, I use the forcing H alpha. Okay, so it means that at the top, this has height kappa. Well, at the top, I'm adding a math family of size kappa. And this A alpha will represent like something in between the step alpha and alpha plus 1. Well, that you add there in between as well. And then you start drawing your finite support iteration. So as I mentioned, you add, this represents the forcing the standard CCC poset that adds an eventually different real. So you add a full generic eventually different real, and you alternate adding restricted dominating reals. So how restricted are they? Well, I think even we can start from the top and choose a small transitive model of C of C of size less than kappa. And then we use just the Heckler forcing restricted to that model. So as this forcing will be quite small, if we construct it at the top as this has size less than kappa and this forcing is formed by reals, as a set of size less than kappa, as this has height kappa, then this forcing actually will live in some intermediate model below. So this is the place, let's say Txi plus 1, the place, actually I choose it as a successor ordinal, the place where this forcing lives, and then we add this restricted Heckler generic, but will be restricted with respect to this very small model that we choose. Well, as I said before, this is to ensure that you don't have small unbounded families. And you just alternate with this, and of course you use, these restricted Heckler generics, you use them by a counting argument in order to ensure that you count all the families of reals of size smaller than kappa. Okay? So alternating this, well, in the top, this have the finite support iteration that I described. So this gives you the division of the Chi-Hun's diagram, well, the proper division of the Chi-Hun's diagram that I showed before. So what about the math family? Well, the point here, I will be like very rough in explaining this. What Brendle-Fisher theory for preserving math families describes is in relation, well, with the successor step. So this A alpha that is added has a special property that intersects all the infinite subsets of omega that doesn't lie on the ideal generated by the previous A alpha things. So here we have constructed, like, I don't know, let's say xi for xi less than alpha. So some fragment from section of this math family. So this will have the property that intersects everything on infinitely many, in an infinite part, everything that doesn't lie on the ideal generated by what you have so far. So this is described even in a more fancier way. So this is, so actually this, the theory says something more general in order that this property that you intersect things that are not in the ideal are preserved through these parallel finite support iterations. And thereafter, then you have that in this column, well, with respect to this column, these A alphas are still preserved as a math family. So this is how it is preserved. So this preservation behaves well in limit steps and also in these restricted successor steps. This is proved in Brendle and Fisher. But what we had in our work is that we could ensure that when we add full generic, in this case, eventually different reals, we could ensure that, yes, that we could preserve this, we could preserve the math family, or in particular the preservation property for A alpha. Okay. So actually, this gives us more general stuff. So morally, this is this finite support iteration constructed here much doesn't depend on the steps below, because here, well, as we are adding a full generic, then the full generic is pretty well described. But here, as this poset is very small, then this poset should lie somewhere below. Okay. So it means that actually the matrix here is just to ensure that you preserve your mod family, but it's not essential for the construction of the finite support iteration. Therefore, we could state something like this. So for a regular kappa, we first add a math family of size kappa using this forcing, and then if we further extend with a finite support iteration, we can preserve this math family. The general proof is as before, but then there you could iterate using these two types of posets. So using, well, adding coherent reals, adding full random reals, or adding full eventually different reals, or just having a small CCC posets. So if you iterate like this, you can always preserve your math family. Okay. So now, so about this example, the point here is that we, in this work, I use a matrix iteration to separate, on the right-hand side, separate the diagram in 3 pieces. So this was not possible before, or at least with linear finite support iterations, like directly, it was not clear how to separate here in 3 pieces. But with a matrix iteration, well, it's possible. Okay. Here I should clarify, okay, Shelah in his talk, he mentioned that he has a model when he divided all the diagram in 10 pieces, which is great. But but of course, well, some improvement needed here is that so far his proof is using 4 strongly compact cardinals. So just if you think on CFC alone, in CFC alone, at least with finite support iteration techniques, we don't know how to divide here in more than 4 pieces, for example. Okay, so this was some model that we had before. But then we succeeded in extending this to a three-dimensional arrangement to have like some further division on the Chi-Huon's diagram, which was not possible to obtain by two-dimensional arrangement. So we additionally could separate here and even more, turning A equals B. So this is something as in the matrix before. So we wanted to include some math family and also give the same examples in finite support iterations. So then we said, okay, if in the previous example that we had a finite support iteration, we have to go to 2 dimensions to preserve a math family, then here for a matrix iteration, then we have to add an additional dimension to preserve some math family if we want to go to that context. But we got even much more, and is that we could have a further division on, when in this case, Chi-Huon's diagram. So I'll try to describe how it goes. Okay. So I will just concentrate here on the part of calculating B and G, because, well, this side that is Aleph 1 and this side that is lambda, it comes from the usual theory for finite support iteration, and this non-meager and cov-meager just come from the full generic, eventually different reals that you add through the iteration. So the iterations will have cofinality mu, and this will ensure this middle part over here. So for the construction, I will just concentrate on the values of B and D. Well, or A and D as well. So how does it go? So we start with this plane, which is the base of our construction. So vertically, we add a math family, and horizontally, we add Cohen reals. And then we go like this. So the iteration will have this length. Okay, it will be a big set, but with a small cofinality. So then, okay, we are at step C of the construction. So one thing we do is to add a full eventually different real. Okay, which is, well, quite well described. Now for the restricted, well, as I mentioned before, we choose some, well, in the plane, in the Xi plane here that we have constructed so far, we choose some of the models here. So this Xi will be some ordered pair referring to your base. And then what we do with respect to, as we want to add a restricted object here, or a restricted generic here, then on this red plane, we extend with some forcing, which only is restricted to this model. And in the remaining area, we just extend using trivial forcing. So what we do is add a dominating real using Heckler forcing. But this dominating real will just be the version of the Heckler forcing with respect to this model, which means that we just add a dominating real over this model over here. Okay? And then the construction goes on, and your final extension is given by this finite support iteration I point in here out in red. So, okay, so first, we look at we alternated these 2 steps of full generics and restricted generics. So the restricted generics are important in the sense that, well, for the size of the iteration. So the cofinality doesn't affect much, but this has size nu. So nu is the size we want to give to B. Okay? So here we are adding these nu dominating reals, and well, actually what we have to ensure is that we can choose these models here properly in order that we can dominate every real by these restricted generics, the restricted dominating reals that we're adding. So at the end, the restricted dominating reals will give you a dominating family of size nu. Okay? So this will keep D low. And on the other hand, you can increase B, because if you have a set of reals living here, a set of reals of size less than kappa, if you look at the dimensions of the matrix, like kappa is the smallest dimension, so if you have some set of size less than kappa, then this set of size less than kappa will live in some model in the middle. So of course, for that you have to ensure that, yeah, that for that model you can go further and then dominate this set of reals. And with that, you can increase B. So now about A, well, we have this math family here. So the point of the construction is that, well, this is in 3D, but when you restrict to some planes, you actually have matrix iterations. So the preservation theory for matrix iterations applies directly here. So the point is that, well, if we look at this plane, this math family that we are here, we can see it as preserved through finite support iterations of co-enforcing here. So this will be a math over here. And then looking at this plane, this will be math over here, which is your final model. So you have a math family of size kappa that you preserve. Now for B, I think what is left is to have D bigger or equal than nu. Well, this is given by the Cohen reals that you add in this direction. So this plane here will give you a matrix iteration. And well, and these Cohen reals that you are unbounded here in this line. But the point is to preserve them unbounded through the iteration. So in my paper of 2013, I dealt with these things for matrix iteration. So looking at this matrix here, or at this plane here, you can ensure to preserve your unbounded reals. And this will ensure to you that D will be bigger than or equal than nu. This can be extended a little bit, okay? Because, well, the cardinals that are here, the additivity of null and the covering of null, if we want those being very small, then you can just include in your iteration small forcings, well, let's say a small amoeba and a small random forcing to increase this enough. And the preservation property of Yura and Shelah will work pretty well for this finite support iteration. So additionally, you can have like these two values in here. And have, you can split the Chihon's diagram in 7 pieces, which is, well, the maximum so far in CFC alone. Okay. And well, I didn't skip all this. So yeah, so this is some sort of example, okay? So now I want to extend this a little bit. So note that for these cardinals, the only one that is singular is this one, okay? And the others must be regular in order for this counting process. So later I will just try to go a little further, and this little bit further will ensure that this can also be singular. So I'm going to aim towards that. So what's next? So, okay, we have 2-dimensional and 3-dimensional arrangements of things. So can we restrict to subsets in an arbitrary way? So this is sort of when you iterate with Suslin CCC posets, you have a finite support iteration, let's say, of Heckler forcing Gaussian dominating real. Then as a Suslin CCC forcing iteration, you can restrict your linear iteration to arbitrary subposet, to arbitrary subsets of your linear order along where you're iterating. So those kind of restrictions are known and even generalized in the context what is known as template iterations. So I wonder whether it's possible to do some similar things to 2-dimensional and 3-dimensional constructions. If we could restrict to an arbitrary rectangle, or if in a 3D arrangement we could restrict to an arbitrary cube. So I will consider several types of restrictions. So of course this describes the general restriction in a 2D arrangement. So if we have a 2D arrangement, then okay, try to talk about restrictions of rectangles. But sometimes something weaker could be also practical, that you only restrict in one direction, okay? So we restrict in rectangles of this form, well, where in the first coordinate is arbitrary, but in the second coordinates is an ordinal. So are like long rectangles, restricting on long rectangles. So this will be practical as well, I will show. And well, and the similar thing for 3D. Restricting to arbitrary rectangles, or restricting to rectangles such that the third coordinate is just long. Okay, so in your 3D arrangement, you have some small rectangle on your base, and then you have a long column where you restrict your iteration. So how do we do this? Well, the direct thing to do is just change your base. So previously, for to construct two-dimensional arrangements, our base was just a linear order. But now our base will be the subsets of this well order, okay? So if we want a matrix of height gamma, okay, so we consider as base all the subsets of size, all the subsets of gamma. And then for each subset of gamma, we define something. So this gives us a lattice of posets, isomorphic to the lattice of the power set of gamma, okay? And this will be the base of your construction. So meaning that you are restricting to a segment on your vertical section will just mean that you are just looking at the subset from when you are extending, okay? So this is the point when I say it gets multidimensional, because now you have a very complicated lattice here as a basis. So yeah, so that's why I think it was not a good title for this talk. So yeah, so one example here is just, well, thinking about adding a math family. So well, for each subset of gamma, we just add the corresponding almost disjoint or math family at indexed by A. And these things are embedded whenever you increase your subset. Well, of course, this respects the structure as well. And this works as a basis for your construction. The same if you use coenforcing, okay? Now for three-dimensional, well, is a similar thing. Now your bases are pair of subsets of your two dimensions. So if for your 3D construction, you start with a plane of dimensions gamma and delta, then you consider the subrectangles there. But instead of subrectangles, I prefer ordered pairs because, well, sometimes one coordinate will be empty. And, well, I think for this type of construction, it's not nice that, well, if one coordinate is empty, then your rectangle will be empty. So this is something that we don't want here. So that's why we just separate on pairs of subsets instead. So the base of the construction will be, well, nicely, yeah. Just in, well, one example, in one direction you are a math family or almost disjoint family using this forcing H, well, with respect to this subset A from the first coordinate, and on the second coordinate you add cohen reals with respect to this set B. Okay? And this respects the structure as well of this order that we are describing here. Same if we use just coenforcing, like adding cohen reals with respect to both directions. So the point here, well, just describing one application. So remember the previous theorem about preserving a math family through finite support iterations. Now, for that family, we don't require that the size of the math family is, we don't require the size of the math family regular. It could be singular, just obeying this equation here. So this equation here just are restricted just to the small CCC posets that you add through your finite support iteration. So if they are small enough, less than kappa, with respect to some uncountable regular kappa, then, well, the cofinality of your math family should be above this kappa, well, bigger than equal. So that's the point. So what's the point on the proof? So it's the same proof as before, but now you consider restrictions. But what will you get from the restrictions? Well, if you are in some large rectangle, like of given by some subset A and of length C, then any condition here actually lives in some suborder where the size of the subset on the first coordinate is smaller than kappa. This means that when you look at names of reals in the same way, every name of a real just lives in some long but not too tall rectangle, okay? And this tricks, then this gives you a space, because then at the end, if you want to ensure that what you have here is a math family, then the name of a real will just, how express this? Or when you have a small set of reals on the top, then they are restricted to some small set. And then you have like this enough objects added by this forcing that will somehow diagonalize that fragment. And then you preserve your mod family no matter if the size is regular. So this is one of the applications. And the other, well, in the same diagram that I described before, is just having this cardinal here actually will become singular, or just restricted to this equation. So this is sharp enough because, well, we know that the cofinality of D is bigger than or equal than B. And, well, and the requirement for this cardinal is more or less that. Okay? So then we can also repeat the construction and obtain what we want. So I will just roughly sketch what are we going to do. So, okay, so we start with a similar base that in the kappa direction we add a mod family, and that in the nu direction we add Cohen reals, like to do the same argument as before. But now, of course, as we are restricting to rectangles, then we look at the versions with respect to the rectangles. So now, how the finite support iterations are constructed? Where we look at a very large well order, but with short cofinality, just to ensure that some values are mu. And then we describe what we do at each interval. Note that here we have nu mu many intervals, okay, which means that we have, well, nu many intervals as well. So I will just describe first what we do to add a restricted dominating. So it's some of the same thing as before. We just choose something in between, and then we add the dominating real with respect to this restricted model. But now what we choose below is a rectangle of size less than kappa. So we just look at some rectangle of size less than kappa, and then we add the restricted dominating real with respect to that rectangle. That will be what we do in the first step of this interval. In the following step, we add a full generic real, which is quite immediate. And then we add just suitable small amoebas and random in order to decide like the first values. I will not describe much about this because it's somehow direct in this context. So the point is about choosing the rectangles. So what do we have to ensure? Well, as at the end, the iteration will have the property that every real will just depend on a small, will depend on a column with some small basis, a small basis of size less than kappa. Then we just ensure that through the iteration we are considering all the subrectangles of size less than kappa from our basis. And well, we also try to repeat discounting cofinally many times in order that every time I have like some small set of reals, then I can cover it with the extension with respect to one of these rectangles that I'm counting. So this will ensure you that you increase D, and also that the dominating family, well, these restricted dominating reals, will give you a dominating family. So the rest will come as described for the example I said before, for the proof I said before. The point here will be this, as in the previous case. So if we have a name of a real in some rectangle, then this name actually lives in some smaller extension when this rectangle has a smaller size. So this is what allows us to repeat the same arguments that we have in using the simple constructions. Okay, so this is just another example that we could get with three-dimensional arrangements, but that additionally we could have this to be singular. Actually, we're restricted only to have cofinality bigger than or equal than kappa. Okay, and there are, well, sort of more examples as well. Okay, now that we are talking to restrictions, so here, for example, in a two-dimensional arrangement, then we just talk about vertical restrictions, but still we have long columns. But what about restricting to just rectangles in the middle? Well, this could be done, okay? It's a bit technical, but in theory you can do it. Still, The applications, well, that it comes from these are actually more or less the same as what we do now. Still, I don't know how to use this in order to get new things, or perhaps this has to be improved to get new things. Well, there is a plan for that. So with this, I was expecting to solve some of the following questions. Perhaps this. So with Martin and Sharon Shelah, we obtained the consistency of this arrangement of Chi-Huon's diagram. The point here is that, well, to increase this one not too much, we have to use we have to add restricted eventually different reals. But adding restricted eventually different reals doesn't ensure you not adding dominating reals. So this construction has to be very careful. And well, the trick there is that along your iteration, you are constructing ultrafilters that helps you calculate some, let's call it ultrafilter limits with respect to the conditions, so that Miller's compactness argument can be repeated to preserve B small. That's like more or less of the point. So of course this worked for B, but I wonder about A. So the preservation of A is like in a matrix form. Okay, so we could think about making this in a matrix form, but it doesn't help because the vertical direction won't refer to a math family. Or also this, or on the other hand, well, if we consider only eventually different real restricted to these ultrafilters, then it's not clear how to preserve some math family. Also, well, related to the previous question, just having something so far. Well, of course, if you have one or two strongly compact, then you can do this, but in CFC alone, well, this is still open. As well as splitting on the left side in many pieces, well, at least like this, is still open in CFC. So, well, another work of Arthur Fisher, Goldstern, Kerner, and Shelah, using creature construction, they could separate many on the left, but as a creature construction, that's omega-omega bounding, so D is Aleph 1. So in particular, in this case, when we want D to be a bit large, well, in CFC, this is considered still open. Okay. So this is sort of all I wanted to say. Thank you very much.